So Tomas told you about how to use Trapdoor claw-free functions for verifiable quantum supremacy and certified randomness generation. And yesterday I told you how to use it for verification, classical verification of general quantum computations. And now the third thing that came out of this was classical homomorphic encryption for quantum circuits. So the question here is whether a classical computer can delegate a quantum computation to a quantum computer on the cloud in a way such that the quantum computer can compute on the data without learning anything about it. So to see this a little bit more formally, you have a classical machine, which is referred to as a client, a quantum machine, who's referred to as a server. The client is supposed to classically encrypt his data and send it over to the server. The encryption serves to hide the data, but we want an added property. We want the server to be able to perform a quantum circuit on top of this encryption. So what the server should be able to do is apply some unitary circuit, maybe in some different way, so that he can obtain the encrypted output of applying the unitary U to the input M. And then he should just be able to send back this encryption. Let's assume the output is classical. He sends it back to the client. The client should be able to decrypt and get the final output. Okay, so this is the model. And now this model is very well studied in classical cryptography, and it's called homomorphic encryption. And here the setting is a little bit different. So now the client is still a classical machine, but the server is a much more powerful classical machine. So now you have a weak client who wants to use a much more powerful server in order to delegate a computation. And the setup is the same in the sense that the client is just supposed to send over encrypted data, and the server should be able to apply a classical circuit on top of that encrypted data. And this question was resolved in 2008 in a breakthrough result by Craig Gentry. And so when you see that we can do this in the classical world, the first question to ask is whether we can take this classical result and use it directly in the quantum setting. So can the client just encrypt his data with a classical homomorphic encryption scheme, send it over to the quantum server, and can the quantum server now apply a general quantum circuit rather than a classical circuit on top of this classically encrypted data? So this approach seems to have an inherent difficulty, and that is that classical homomorphic encryption schemes require that each bit has many different encryptions. And this is intuitively, it's because with the classical homomorphic encryption scheme, you're able to compute a circuit on top of the encryption. And if the encryption is deterministic, maybe you can compute many different circuits and then compare the final encryptions to learn which are the same and which are different, and this might reveal something about the input. So this is why it's required for classical homomorphic encryption schemes. But then there's also the quantum property of interference. And what it seems like is this multiple encryptions seems to ruin interference. So now let me tell you why, or let me try to tell you why by giving you an example. So I think all of you here know what the Hadamard transform is. It's just a reflection by pi by 8. So it maps 0 to the uniform superposition over 0 and 1, and it maps 1 to the uniform superposition over 0 and 1, but with a phase of -1. And what interference says is that elements of a superposition, which represent the same bit string, but with opposite amplitudes, have to cancel. So to see this with the Hadamard transform, we know that the Hadamard transform of the plus state is 0. But to break it down, I can just write it out. So the Hadamard transform is 0 plus 1, and 1 is 0 minus 1. And interference is just saying that the two 1s cancel. So now let's say we try to use classical homomorphic encryption schemes in the most obvious way. So we just took these 0s and 1s, and we replaced them with encryptions of 0 and encryptions of 1. So it would look like this. Now, the problem is, what I said earlier is that the encryption of 1 can be many different strings. And so there is no guarantee that these two encryptions of 1 will cancel. So I don't know that this expression will evaluate to the encryption of 0. And that's the problem. That's what I mean when I say it interferes with interference. Okay, now, due to this difficulty, we didn't know how to extend classical homomorphic encryption schemes to quantum computation, and we weakened the original model slightly. So I originally told you that I want to have a classical client delegating a quantum computation. But instead, we studied the model where the client is a weak quantum machine. So now the client is a weak quantum machine, and the server is a more powerful quantum machine. And the goal is the same. You want to delegate a quantum computation so the server can't learn anything about it. Now, this question was studied in 2 different settings. In the first, the model was relaxed a bit further to allow multiple rounds of interaction between the client and the server. This was called blind quantum computation, and it was first shown to be possible by Andrew Childs in 2005. So he showed that a weak quantum client can blindly delegate a quantum computation with information theoretic security. So there were no assumptions. And then this model was strengthened to the point where the client required only a single qubit quantum register. So the client was so weak that all he had to do was be able to work with single qubits at a time. He still had to send over polynomially many, but at any given time, he was only working with 1 qubit. And then these results were strengthened even further by Dweck, Schaffner, and Spielman in 2016. And in their result, they removed interaction entirely. So now the client just sent over 1 message to the server, and the server responded. But this came at the cost of replacing information theoretic security with computational security. So now it was assuming something like the quantum server cannot break learning with errors. So this line of work was extremely interesting, and it advanced the field of delegated quantum computation significantly. But the problem is with the quantum client. So this is a significant issue because the reason the quantum client is needed is because the quantum client has to create quantum evaluation keys which assist the server in performing the computation. So the server takes these evaluation keys and he needs them to apply gates on top of the encrypted data. And there's 2 issues with this. So this is the reason the client has to be quantum, because he has to send these keys. And the 2 issues are, first, that the number of evaluation keys grows with the size of the circuit rather than the depth. And the second is that quantum keys are inherently not reusable. Because when the server uses them, he measures them, and now the next time he wants to run a circuit, the client has to generate fresh evaluation keys and send them over. So to put all of this together, what I've said is that each time this quantum client wants to delegate a quantum computation, he has to run a quantum computation of roughly the same size as a server, because he has to create all these evaluation keys. So what we would really like to do is significantly cut down the power of the client so he doesn't have to do this. And that's why I'd like to return to the original question with a classical client and a quantum server. And in this talk, what I'll show is that certain classical homomorphic encryption schemes can be used to evaluate quantum circuits. So I'll show that the client can just use a classical homomorphic encryption scheme if it satisfies certain properties, and he can encrypt his data, send it over to the server. The server can apply a quantum circuit on top of this data and send back the result. And now, if you remember, I said earlier that there were obstacles to this, and that had to do with interference and multiple encryptions. And I'm going to get around these obstacles by showing that if the scheme satisfies certain properties, these obstacles are not an issue. So since I'm using classical homomorphic encryption schemes, I inherit the same benefits. First of all, the keys are reusable. They're classical keys, so I have no concern with the quantum system measuring it. And for those of you who know a bit more about crypto, I also have something called circular security, which means I can get pure, fully homomorphic encryption by assuming circular security. And this scheme is the first to allow blind quantum computation between a classical client and a quantum server, because all of the previous schemes were in the quantum client model. Okay, so in this talk, I'm not going to have time to show you the full encryption scheme. So what I'm going to do instead is focus on the core of my protocol, which is called the encrypted CNOT operation. This is the part of my protocol that's new. So the rest of my protocol follows the same structure as the previous schemes, but I take this core object and I build it in a different way. And that's what enables the classical client. And so in all the previous results, they showed that quantum homomorphic encryption boils down to this operation, which I'll tell you about now. I can't tell you why, but I'll ask you to take it on faith in this talk that all we need for quantum homomorphic encryption is this encrypted CNOT operation. So now let me define what the encrypted CNOT operation is. To do this, I first should remind you what the CNOT gate is. It's the reversible XOR gate. So if you look at this picture, it's just taking A and B, and it's XORing A into the second register. Okay, the encrypted CNOT operation is a controlled version of this gate where the control bit is an encrypted bit. So it's a classical ciphertext encrypting a bit. So here's what it looks like. Well, okay, so the encrypted CNOT operation means that the server is given a bit S encrypted under a classical homomorphic encryption scheme, and he should either apply the CNOT or not based on the bit S. So he's taking this hidden bit S and conditionally applying a quantum operation. So here's the picture of it. So now the first wire is the encryption of a bit S, and the second looks almost the same, but if you look at the last wire, A.S, so if S equals 0, nothing happens. If S equals 1, then the server should be performing the CNOT operation. And this is what it looks like on a state in superposition. So what I require is that the server has to be able to perform this encrypted CNOT operation, which has this functionality. Okay, so now that I've written it down, let's look at it a little bit closer. So the first thing to note is that what I've written is impossible, because if the server could do this to an arbitrary 2-qubit state, then of course he could set B equals to 0, A equals to 1, and he could learn the bit S. So he could use this operation to violate the security of the encryption scheme. So I will require that the output is suitably encrypted, but I'll get more into that in a second. But the thing to notice about this operation is the server is taking as input a classically encrypted bit, which he cannot see, and he's converting it into a quantum operation. So that's why it's interesting, because he can't even see this bit, but he's able to apply a quantum operation or not based on it. And this makes sense, because what I want is a classical client to send over encrypted data and a quantum server to apply a quantum circuit based on this data. So he has to be able to apply a quantum circuit or not based on a hidden bit. So that's what's happening in this operation. The server is converting a classical ciphertext into a quantum operation. And now, so I need to tell you what it means to be suitably encrypted, because as I've written, this is not possible. So I need to tell you how this is actually done. So let me tell you what it means to be suitably encrypted, and I'll use something called the Pauli one-time pad. Oh, so one more thing about this. The reason this is interesting is because all previous work reduced to the same operation. So they all knew that you had to do, like in Dulac, Schaffner, Spielman, they knew that you had to do a controlled operation based on a classical ciphertext. But before, it required a quantum evaluation key to be sent to the server in order for him to be able to convert a classical ciphertext into a quantum operation. And here what I'm showing is that the ciphertext is enough. So he doesn't need any additional help from the client. He can just look at the ciphertext, and if it satisfies certain properties, he can convert it into a quantum operation. Okay, so now let's cover the suitable encryption. It's called the Pauli one-time pad. This is an information theoretic encryption for quantum states, and I'll show you how it works for a single qubit quantum state. So the first step is to sample a bit Z at random, and then apply the Pauli phase operator. So the Pauli phase operator just adds a -1. So if Z equals 0, nothing happens. If Z equals 1, you get a -1 phase. The second step is to sample a bit X at random and apply the X Pauli operator, which is just the classical one-time pad. So it flips 0 to 1 and 1 to 0. So at this point, this is what the state looks like. And now it's pretty easy to show that if a bit X and a bit Z are both sampled uniformly at random and applied to a quantum state, the resulting state is the maximally mixed state. So it's the identity matrix. So this information theoretic method of encryption entirely hides the quantum state. What I need is a computational version of this, and in a paper by Broadbent and Jeffrey, they showed how to convert this into a computational encryption. And what they did was, now they have a two-part encryption. They have a one-time padded quantum state, and then they have the classical encryptions of the one-time pad. So this is a commonly used technique in cryptography. So this is what the encryptions that I'll be working with look like. You have the one-time padded quantum state, and you have classical encryptions of the one-time pad. These classical encryptions are under a classical homomorphic encryption scheme. Okay, so now that you have the encryption that I'm going to use, let me try to give you a better picture of what the homomorphic encryption scheme looks like. To encrypt his data, the client just applies a one-time pad to the input quantum state, and then he also encrypts the one-time pad keys. So this might be a little confusing because I originally said the client was classical, but now it looks like he's doing a quantum operation. But the thing to note is that if psi is just a standard basis state, then when you apply a one-time pad onto it, it's just doing the classical one-time pad to a classical bit string. So in the case that psi is a standard basis state, this one-time pad encryption is just a classical string. So in that case, everything would be classical. Okay, and then, so I'll just tell you this, but I can't go into details. So quantum homomorphic computation, the way the server computes on the ciphertext is by doing a quantum computation on the one-time padded state, which is dependent on the classical keys. And he also does a classical homomorphic computation to update the keys as he's going along. Okay, that's all I'll say about that. But now, remember I told you that everything reduces to the encrypted CNOT operation, and I asked you to take that on faith. So now let me write down what the encrypted CNOT operation is in terms of the Pauli one-time pad. So the server takes as input a bit S, an arbitrary 2-qubit state psi. The bit S is encrypted. What he needs to do is conditionally apply the CNOT to the 2-qubit state based on the bit S. And now the suitable encryption is just the Pauli one-time pad, the computational version of the Pauli one-time pad. So there's this one-time pad, and the server can also compute the encrypted one-time pad keys. Okay, so this is the full picture of the scheme. I can't get into the details of the first bullet point, and for the rest of the talk, I'm going to focus on the encrypted CNOT operation, and I'll tell you how the server can perform it. So just like Tomas, I'm going to rely heavily on trapdoor claw-free function pairs in order to build the encrypted CNOT operation. And since he just told you about it, I'm going to go through this a little bit more quickly. I'm just going to remind you of the definition. So a trapdoor claw-free function pair is a pair of functions which are injective and they have the same image. There's a trapdoor which allows for efficient inversion. So given a trapdoor and an image y, there's an efficient algorithm which outputs the two pre-images of y. And finally, there's the claw-free property, which says that it's hard to find a claw, which is a pair of pre-images mapping to the same point, as long as you don't have the trapdoor. So this claw-free property should hold for both quantum and classical machines. And now the reason that these trapdoor claw-free functions have been so interesting is because a quantum machine can sample a random image y and create a uniform superposition over the corresponding claw. So this was used in the randomness and in verification, and it will also be used here. And the way he does this is by creating a uniform superposition over the domain, applying the function in superposition, and measuring the final register to obtain an image y, which collapses the state to a superposition over the pre-images. Okay, so this is all I'm going to say about all I'm going to say for the setup of trapdoor claw-free functions. And now I'm going to show you how they are used to build the encrypted CNOT operation. So I'll show you how they're used in order to allow the server to convert a classical ciphertext into a conditional quantum operation. And the way I do this is I use a trapdoor claw-free function pair to encrypt a bit S. And I'll tell you what that means in a second, but if this encryption is of this special structure with a trapdoor claw-free function pair, then this conversion to a quantum operation is extremely easy for the server. And essentially all he has to do is take his state and entangle it with a claw, and he's done. Okay, so now I'll tell you what it means for a bit to be encrypted by a trapdoor claw-free function pair. So the encryption of the bit will just be a trapdoor claw-free function pair. So this encryption of S will just equal F0, F1. And now what I've done here is I've written the function pair a little bit differently. I just split up the domain. So the first part is a bit, and the second part is a finite set R, and the image is a finite set Y. And now these first two conditions are saying that the function pair is a trapdoor claw-free function pair. Injective, same image, trapdoor, hard to find a claw, I use different notation for the claw. mu0 and mu1 are bits. They're from the first part of the domain. r0 and r1 are from the second part of the domain. And now, so far, it's just a trapdoor claw-free function pair. But to make it an encryption, I'm going to hide the bit s in the XOR of each claw. That's why I split up the domain. So now, in the first bit, for all claws, mu0 XOR mu1 equals s. So this is what makes it an encryption of a bit s, because s is hidden in each claw. And so to find s, you'd have to find a claw. I'm skipping a detail here because it's not hidden in the whole claw, it's only hidden in the bit. So this is a little bit subtle, but I'm not going to get into that here. Let's just think of this as an encryption of a bit s. Okay, so now, given this encryption, how does the server compute the CNOT conditioned on the bit s? So remember, this is his goal. He's given the encryption of s, which is a trapdoor claw-free function pair, and he wants to apply CNOT to an arbitrary 2-qubit state conditioned on the bit s. Now, I'm just going to simplify things a little bit. I'll just set b equals to 0, just so it's easier to see what's going on. Okay, so here's how he does it. All he does is he uses f0 and f1 to sample a random image y and entangle his input state with the corresponding claw. So this is done in the same way. He creates a uniform superposition over the domain. He applies the function in superposition. He measures the output of the function. And now he just has the input state entangled with the claw. And I claim that this essentially completes the encrypted CNOT operation. And here's why. So remember, a trapdoor claw-free encryption hides the bit s in the XOR of each claw. So if you can, so right here, I'm writing mu0 XOR mu1 equals s. That's the condition that the trapdoor claw-free function pair satisfies. And I can rewrite that in this way. Because if a equals 0, then you get mu0 equals mu0. And if a equals 1, you get mu1 equals mu0 XOR s. So I've just rewritten it. And now, when you entangle a state with a claw, you are essentially XORing a.s into the second register because of the fact that s is hidden in the XOR of each claw. So this is pretty much it, because if you compare this third line to the first line, they look almost the same, but they're off by these parameters mu0 and ra. But remember, I told you that there has to be a suitable encryption. You can't just have a.s in the clear because it will leak information. And that's essentially what mu0, r0, and r1 serve. That's the purpose they serve. So mu0 is a classical one-time pad because it's just a bit flip. And r0 and r1 are necessary because the bit s is stored in superposition. So just a classical one-time pad is not enough to hide it. And r0 and r1 can be turned into Pauli z operators. So if the Hadamard transform is performed on this register and it's measured, it can be turned into a z operator. I'm not going to get into those details here. So I know that this was a little bit technical, this slide, so let me try to recap what just happened. This is the encrypted CNOT operation. And what I wanted to show you is that it's easy to do if the encryption of s is equal to a trapdoor claw-free function pair, which hides the bit s in each claw. So this is the input-output behavior that the server should be able to perform. And the way it went was that the server uses f0 and f1 to entangle the input state with a claw. And the result of this is a.s is stored in superposition because of the fact that mu0 XOR mu1 equals s. And then the second step was just to say that mu0 is essentially an x Pauli operator, r0 and r1 are z Pauli operators. So he's basically done with the operation. So, okay, so this was how to perform the operation with a special encryption, which was a trapdoor claw-free encryption. But if we go back, what I initially said when I told you about the scheme was that the encryption of s has to be a classical homomorphic encryption scheme. That's what I required. But all I've shown you is how to do it if it's a special trapdoor claw-free encryption. So the last step of this protocol is how do you link the two? Now, So what I'm asking is, are there classical homomorphic encryption schemes for which the encryption of a bit S is just a trapdoor claw-free function pair? Unfortunately, it doesn't seem like people in classical cryptography really care about this, so I can't see that. But there's a different way of asking this question, and it's saying that if the server gets as input the encryption of a bit S under a classical homomorphic encryption scheme, can he, by himself, produce the public key or a method to evaluate this trapdoor claw-free function pair F0, F1? Because if he can take as input a ciphertext and figure out how to evaluate a trapdoor claw-free function pair hiding the bit S, then he's done. Because now he can use the ciphertext to do the encrypted CNOT operation. Okay, so this is the question, and it turns out that yes, this is possible for the server to do if the scheme satisfies certain requirements, which happen to be well-studied requirements in classical homomorphic encryption schemes. And these requirements can be formalized to define something called quantum-capable classical homomorphic encryption schemes. And by that, I just mean classical homomorphic encryption schemes for which it is possible to evaluate a quantum circuit homomorphically. And finally, it turns out that there is a scheme in literature which satisfies these requirements. And this scheme can be obtained by combining two existing schemes in literature. And what that means is that this specific scheme can be used to evaluate quantum circuits. Okay, so to put everything together, I've shown you that I first told you that quantum homomorphic encryption boils down to something called the encrypted CNOT operation, which is the ability of the server to convert a classical ciphertext into a quantum operation. And the quantum operation specifically is the CNOT operation. Then I told you that this encrypted CNOT operation is easy if the bit S is encrypted using a trapdoor claw-free function pair. And what this means is that the bit S is hidden in the XOR of each claw. And if this is the case, then the server can take this bit S and convert it into a quantum operation just by taking a state and entangling it with a claw. And then the final step was to link everything together. So we started with classical homomorphic encryption schemes encrypting the bit. I said it was easy if a trapdoor claw-free function pair encrypts the bit. And then I connected the two by saying that a classical homomorphic encryption scheme can be converted into this trapdoor claw-free encryption if it satisfies certain properties. And I called those schemes quantum capable. And then I told you that such a scheme can be constructed from schemes existing in literature, which are based on the assumption of learning with errors. So to put it all together, what I've told you is that blind delegation of quantum computations by a classical client is possible, assuming the quantum security of learning with errors. Okay, thank you.
Okay, thank you, Mila. Questions?
So you said that our function encrypting the bit S needs to be a claw-free, needs to be a, right, the function pair encrypting the bit S needs to be claw-free. But it doesn't seem like just from claw-freeness you get a guarantee that someone can't find the first bit of a claw. Do you need an additional assumption there?
If I was going to define it like that, then yes, I would need an additional assumption, but in the paper, I convert it differently, so this was just trying to simplify the picture. So in the paper, I don't go through trapdoor claw-free function pairs. I just take the classical homomorphic encryption scheme and show that if it satisfies certain properties, then you can do this. So, yeah.
So would you please comment on any high-level similarity or difference between what you use here for the FHE and what you use for delegation? Both using claw-free function, but one is...
Sorry, for verification, you said?
For delegation.
Okay.
Yeah, so you both use a claw-free function, but one is to encode a qubit, but here is the encryption of classical sense, allowing you to do encrypted quantum operation.
Right.
But there's apparent similarity, but I just want to see how would you comment the similarity and difference between those two?
Well, the tasks are entirely different. Because here I'm just hiding information and in one I'm verifying. And I think the way the difference comes out is because in verification and randomness generation and verifiable supremacy, we needed something called this adaptive hardcore bit requirement. And that's really what allowed us to control the prover. Where here, I don't need that requirement because all I'm doing is hiding and not controlling. So in this paper, I don't use the same construction of trapdoor claw-free functions. I use a different construction which I build directly from classical homomorphic encryption schemes. Yeah.
So in classical homomorphic encryption, there's a concept of error that creeps in with every iteration. How does that map to this this scheme?
That's something that came up really specifically, actually. So essentially the error, in the very beginning, I told you that there's this problem with multiple encryptions and interference, and that really comes from the error, because the error is what makes all these ciphertexts different. So what I said is that if this classical homomorphic encryption scheme has really nice properties with respect to the error, then it can be used. So this is something that cryptographers call circuit privacy, where they can twist the ciphertext in such a way that the distribution of error is independent of the data that's encrypted. And so the error is a huge part of it, and that's what I need. Yeah.
Yes. An encrypted CNOT appears to be asymmetrical to Foley gate, correct?
Asymmetric to what?
It's a two controls. It's a Foley gate, which is asymmetrically controlled.
Yes.
Now, it seems to me that a straightforward decomposition of this into ordinary CNOTs is going to be creating a situation where the other qubits in the system are entangled with each other. Do you see any way to decompose an encrypted CNOT into ordinary CNOTs without having the output results be entangled?
Maybe we should take this offline, because I'm not sure I understand your question.
I'm trying to break the security of the system by decomposing the gate setup, but thank you.
Yeah, sorry. I'll catch up with you. Yeah.
So classical homomorphic encryption has like notoriously very high overheads. To what extent does the server have to pay that in kind of the quantum bit of his computation? And to what extent is it just in the classical bit? Okay,
so it is mostly in the classical bit, but whenever he wants to do this encrypted CNOT operation, then he essentially has to apply the encryption function of the classical homomorphic encryption scheme in superposition. So that's the extent to which they overlap.
So you sort of pay the overhead of the encryption, but not of the operation?
Yes.
Okay, let's thank Urmila again.